Okay, folks, so here we are with the second example. That will be just a little bit harder than the last one, and you'll see why very shortly. So let's read through it and then work on developing a strategy to solve. So let's read it. So the molar solubility of silver chromate, here's our formula, in pure water is 6.7 times 10 to the negative 5 moles per liter. So what that means is that if I had a liter of solution, 6.7 times 10 to the negative 5 moles of silver chromate, this guy, would be able to dissolve. So that's how many moles of that solid would dissolve. And so the question now goes on to say, what is the Ksp for silver chromate? All right, so let's start with what the question is asking. The question is asking us for the Ksp value. So I'm going to go ahead and write out my reaction equation so that I can easily fill in an equilibrium law for this solubility product of Ag2CrO4. So watch me go. Okay, so I have my Ag2CrO4, and I know that the 2 subscript beside my Ag is there strictly because of the charge on CrO4, my chromate ion. Okay, and the charge on Ag is +1. So I know that when I show the dissociation of Ag2CrO4, I'm going to have to show 2 Ag pluses. And it wouldn't make sense for me to have anything but, because I need to have ions on the right side and the atoms within the molecule on the left side. Since I have 2 silver atoms, it means I need to have 2 silver ions as well. Okay, so along the same vein, I'm going to show my chromate ion as CrO4 with a 2- charge. And so now I'm ready to write out my Ksp expression. So Ksp is going to be equal to my concentration of Ag plus squared times the concentration of CrO4 2-. And you may be thinking, well, why has she not included the Ag2CrO4, the silver chromate, in there? Well, remember that we're talking about a solid that's dissociating into ions. And so as a result, the ions are going to be written into the equilibrium law, but the solid is going to be excluded. Okay, so we know that somehow I need to know how much silver ion and how much chromate ion are going to be present in equilibrium if I'm going to find out my Ksp value. So I'm just going to put these aside for a little bit. Woo. Over here, and I'm going to think about how to fill in my ice chart. Alright, so again, any solids excluded from the equilibrium law. I know that I'm starting with 0 ions in solution, and I know that my silver is going to increase by 2x because its coefficient is 2. And I know that the chromate ion is going to increase by x because its coefficient is 1. And I also happen to know that at equilibrium, the molar solubility is 6.7 times 10 to the negative 5. So that tells me that since I know that for every 1 silver chromate, I produce 1 chromate ion, I know I'm going to have exactly 6.7 times 10 to the negative 5 moles per liter of chromate in solution. Okay? And looking at this mole ratio, it's a 1-to-2 ratio between my silver chromate and my silver ion, so I'm going to have exactly 2 times 6.7 times 10 to the negative 7 moles per liter of it. So now I've got all substitute this into my equilibrium law. And so I'm going to do that into my solubility product. I'm going to move this back up again and leave some room for me to write in my solution. So I have 2 times 6.7 times 10 to the negative 7. But that has to all be squared because the expression says it needs to be squared. And I'm going to multiply that by 6.7 times 10 to the negative 5. Oops, made a mistake over here. This should be a 5 and this should be a 5. So working all of that out, I will get my solution. I'm getting 1.2 times 10 to the negative 12 and add to the negative 12 as my Ksp value for this problem. All right, so here is the flip side of what we just saw, where we actually know the Ksp value, and we're asked to find the molar solubility. So that is, how much of our solid is actually dissolved in solution. So since they tell us our solid is AgCl, we're going to write out its dissociation, and it has to be a balanced chemical equation. And I'm going to fill in my ice chart as usual. So my solid, any solids, are going to be excluded from the equilibrium law. Okay, I'm going to start out with 0 of each of my ions, but they're both going to increase. And based on the coefficients in the balanced chemical equation, I'm going to see them both increase by x. So since I don't know the molar solubility of AgCl, that's what I'm finding out, I can't solve for x. So I'm simply going to write out x and x as my equilibrium concentrations right now. Okay, so this is actually quite a simple question. I want to write out my equilibrium, my solubility product expression out. So my Ksp in this case is going to be equal to the concentration of silver ions times the concentration of chloride ions. And in this particular question, they've given me the Ksp outright. Okay, and they don't tell me the temperature, so if it doesn't match the one that's in the table at the back of the book, it may be because the Ksp was measured at a different temperature. Okay, but if the question doesn't give you a Ksp value, then you're safe to go ahead and look up the reference value in the table in the back of your textbook. Okay, so 1.8 times 10 to the negative 10 is equal to, well, x times x. I'm going to go ahead and replace that with x squared. And so it appears to me that in order to solve for x, I just need to simply take the square root of both sides of my equation here, and that will give me x, the value of my unknown. I'm going to quickly solve for that. I'm getting that x has a value of 1.3 times 10 to the negative 5. And remember, x represents a concentration, so the units are moles per liter. And so now let's examine what x signifies. X signifies the concentration of both my silver and my chloride ions. But I need to remember that those are in a 1-to-1 ratio with my solid. So that if I know what the concentration is of my ions in solution, I also know my molar solubility of Ag. So yeah, so I can say therefore the molar solubility of AgCl is 1.3 times 10 to the negative 5 moles per liter.